Now I'd like to show you a couple of definite integrals involving logarithms. Both of these are problems from the textbook. First of all, let's look at number 54, which is the integral from e to e squared 1 over x log x dx. Now sometimes when you're doing u substitutions, the first thing you try might not work. Let me show you. In this one, it would be perfectly reasonable to think, well, maybe I can let u equal the whole denominator. U equals x log x. Let's just see what that attempt would look like. If you let u equal x log x, then the differential of u is going to be the derivative of x log x times dx. So using the product rule, I would have 1 times log x plus x times 1 over x dx. In other words, I would have natural log x plus 1 dx. And notice that there's nothing looking like that du in our problem. There's no way I can just multiply and divide by a number and get a natural log x plus 1 dx. So we tried, that one didn't work. We need to try something different. It turns out that simply setting u equal to natural log x will work in this problem. If you let u equal natural log x, then du is 1 over x dx. And notice that I do have a 1 over x dx in this problem. So let me start rewriting it a little bit. I can rewrite 1 over x log x as 1 over log x times 1 over x dx. And then I see that this part will take the place of du. Now I do need to change the bounds. X is going from e to e squared, but u is not. If x is equal to e squared, then u is natural log of e squared. And remember, natural log of e squared is 2. The log and the exponential cancel because they're inverses of each other. And if x is equal to e, then substituting in, u is natural log of e, which is 1. So now let's translate this into an integral involving u. The 1 over x dx becomes du. The 1 over log x becomes 1 over u. And u goes from 1 to 2. Now the integral of 1 over u is natural log the absolute value of u. And we're going to take that from u equals 1 to u equals 2. So when I substitute the endpoints and subtract, I get natural log of 2 minus natural log of 1, but natural log of 1 is 0. So my final answer for this first example is natural log of 2. Now let's look at an application problem in the book which involves a definite integral. And that's problem number 68. Here they ask you to find the area of a region using a definite integral. And I'll sketch the region. It's the graph of y equals sine x over 1 plus cosine x, which they say has a graph something like that. And they specifically want the area underneath that graph between pi over 4 and pi over 2 on the x-axis. Oh, sorry, pi over 4 and 3 pi over 4. So they want the area of that region. Well, remember, if you want to find the area underneath the curve, then you integrate the equation for that curve, which in this case is sine x over 1 plus cosine x. And the x bounds become the bounds on the integral. So we'll be integrating from pi over 4 to 3 pi over 4. Now this one's a great candidate for a u substitution. Notice that the numerator is very similar to the derivative of the denominator. So if I were to set u equal to 1 plus cosine x, notice that du would be negative sine x dx. And I have a sine x dx, so I can easily multiply by negative 1 to get the du that I need. So let's just rearrange things a little bit. I have the integral from pi over 4 to 3 pi over 4 of 1 over 1 plus cosine x times sine x dx. And then I'll multiply by that negative 1 and multiply by another negative 1 to cancel it out. Negative 1 times negative 1 is 1. And all of this, the negative 1 sine x dx, is going to be du. So what I have so far is negative the integral 1 over u du. Let's figure out what the u bounds are. X goes from pi over 4 to 3 pi over 4. Let's see what u does. If x is equal to 3 pi over 4, then u is 1 plus cosine of 3 pi over 4, which is 1 minus 1 over square root of 2. If x is equal to pi over 4, then u is 1 plus cosine pi over 4, which is 1 plus 1 over square root of 2. Now to make things a little bit easier in a little while, let me maybe write this as square root of 2 over 2 instead of 1 over 2, 1 over square root of 2. Well, that's kind of gross. So my bounds are from 1 plus square root of 2 over 2 on the bottom to 1 minus square root of 2 over 2 at the top. Notice that I have the larger bound on the bottom and the smaller one on the top. So I think I want to swap those two bounds and get rid of that minus sign. So let me write this here before I go back to the top. It'll be positive the integral from 1 minus square root of 2 over 2 to 1 plus square root of 2 over 2, 1 over u du. The antiderivative of 1 over u is natural log of u, natural log absolute value u. And this is going to go from u equals 1 minus square root of 2 over 2 to u equals 1 plus square root of 2 over 2. So I get the answer natural log of the absolute value of 1 plus square root of 2 over 2 minus natural log absolute value 1 minus square root of 2 over 2. And that is a perfectly respectable answer. So you could stop here. I'm just going to point out, though, that the book doesn't stop there. They do a bunch of algebra so that they can write the answer in a different way. Just so that you can see what that algebra looks like, I'm going to go a little bit further, just to show you the arithmetic they use. First of all, let me get a common denominator inside each of these logs. The common denominator would be 2, so I can write 1 as 2 over 2 in each case. So I have 2 plus the square root of 2 over 2. And over here, I have 2 minus the square root of 2 over 2. Notice that both of these are positive numbers, so I don't really need absolute values. I can just use parentheses. Now remember when we first introduced logs, I reminded you that the quotient rule applies, that natural log of A minus natural log of B is the same as natural log of A over B. So I can say here that this difference of logs is the same as the natural log of the quotient of those two functions, or quotient of those two numbers. Now, of course, to divide fractions, I can multiply the top fraction by the reciprocal of the bottom. So I get natural log of 2 plus the square root of 2 over 2 multiplied by 2 over 2 minus the square root of 2. And the 2's cancel. And I get natural log of 2 plus the square root of 2 over 2 minus the square root of 2. And look at that. That's much nicer. But the book doesn't stop here either. The book keeps going. So let me show you what they do next. The next thing they're going to do is rationalize that denominator. So they're going to multiply top and bottom by 2 plus the square root of 2. Let's see what that does for us. Coming back up to the top. On top, I'm going to FOIL out. So I have 4 plus 2 square root of 2 plus another 2 square root of 2 is 4 square root of 2 plus square root of 2 times square root of 2 is 2 over, on the bottom, multiplying out, 2 times 2 is 4 plus 2 root 2 minus 2 root 2, those cancel out, minus square root of 2 times square root of 2 is 2. So I have natural log of 6 plus 4 square root of 2 over 2. And notice I can divide that 2 into each term in the numerator to get natural log of 3 plus 2 root 2. And you've got to admit, that is a prettier answer than the one that we wrote down earlier. But definitely, you don't need to worry about writing it in this form on your homework or on your exams.